Hey everyone, and welcome to the next session on Wipro's round 2 preparations towards technical concepts. We in our previous sessions have gone through a lot of concepts, particularly from C, C++, Java, and all object oriented concepts that can be asked, all object oriented programming concepts from polymorphism and so on. So if any of you have missed out on the previous videos, do check out our previous videos, subscribe and check them through so you don't miss out on any of the content. So from here, in our current session, we're going to look at mainly concepts of data structures and algorithms. We will not be going in depth into the coding part of this, but we will mainly be looking at all the concepts that can be asked when it comes down to data structures and algorithms from the face-to-face interview point of view. Now, in the last session, we just looked at a couple of basic things like what is a data structure and why are there so many data structures that we can use. So to begin with, in short, a data structure is just a way to store data and use it efficiently. Now, when we talk about using a data structure efficiently, there are two ways which define this word that is called efficiently. It is defined by the time that it takes and the memory that it takes. In terms of memory, we also call it as the space that it takes. So, this is generally termed as time complexity, and this is generally termed as space complexity in most of the books, tutorials, and so on. So let us take one example to understand how this time and space complexity work. What are they? Because when we talk about data structures, one of the first questions you can often expect is following by what is a data structure and why are there so many data structures. We got to know why are there so many data structures because each data structure focuses on time as well as memory or space in a different way. And the data structures that we are going to learn, we will see how they either use time as the major concern or space as the major concern. Now, since we got to know why there are so many data structures, let's now learn one more important part that again is often asked as an interview question. How do you measure space complexity and time complexity? Because you can't say that you can measure time complexity by how many seconds it takes, because if you talk about how many seconds it takes in terms of time complexity, think about this. I have let's say an i3 processor, and a friend of mine, let's assume, has an i7 processor, which is, let's say, 10th generation, and let's say the one that I have is, let's say, 7th generation. Now, when you measure time complexity in terms of seconds, this is going to take lesser seconds to run the same amount of same lines of code, whereas this computer is going to take more seconds to run the same code. So you can't say it can be measured in terms of seconds because each computer takes different number of seconds to run it. So time complexity is instead measured in number of operations. It's always measured in number of operations. Take this for instance. Let's say I have a for loop. Let's just take instances for I equals 1, I less than equal to, let's just take 1000, and I plus plus. Now here, 1000 times, let's say I'm repeating some statements of code. Now this statement of code, whatever is repeated 1000 times, it will run for different amount of seconds in my computer to different amount of seconds in a friend's computer, depending on the hardware configuration. So instead of that, the way we do measure it is using number of operations. How many times is this statement executed? This statement is executed exactly 1000 times. Since it is executed 1000 times, immaterial of how many seconds it takes, we do not consider the amount of seconds this statement takes, whether it takes 1 second or 10 minutes, it doesn't matter. But these statements, whatever we have, are executed 1,000 times. This number of operations is often considered to identify time complexity. And that is exactly what we will do here in order to identify time complexity. To understand this in short, let us try finding time complexity for a simple data structure so that we can learn the same and try to see how it is implemented in real cases. The example I will take here is a simple data structure, that is array. We know how arrays work. And when we talk about time complexity, there are three particular cases that we need to know. There is something called best time complexity, average time complexity, and worst time complexity. So for every algorithm or for every code, it can execute quickly or on an average time or in the worst case scenario. To understand this, I'm just going to take one simple analogy and then we'll go ahead with our example of arrays. Take for instance, you are going from your home over to, let's say, your friend's home. Now, if you travel at 9 a.m., which is the peak hours, it's going to take the longest time. So you can say that is the worst condition or worst time complexity. And worst time complexity is measured with big O of number of operations. How many operations would exactly need to be done? So followed by worst case time complexity, the next thing that we have here is average time complexity. Average time complexity could be something like 12 p.m. or something like that, where the traffic isn't so much. And average time complexity is often measured using theta. So theta of number of operations. This is used to measure average time complexity. And finally comes the best time complexity. Now the best time complexity is when you travel something at 3 a.m. where there's literally no traffic. You can easily travel without any issue. So this is measured by omega of the number of operations. Here the number of operations may be n, maybe 2n, maybe 3n, anything. We'll see why numbers come up as n, 2n and so on over there. Now worst time complexity can also be, instead of 9 a.m., let's say for example, you're traveling at 3 a.m. itself. Of course, it's the best case time complexity when it comes to traffic. But let's assume you run out of fuel in between, and you have the nearest fuel station is far away. So you will not be able to make it to your friend's place. You'll probably have to go back home in that case. So worst time complexity can also be that you're unable to finish the entire process at all. So this is how we generally measure them, and as programmers we always need to calculate worst time complexity, because we need to know in the worst case scenario how long will our program take to function. So let us try figuring out and let us try calculating how exactly this works. So before this, let's just state this down. There's something called best time complexity, which is measured by theta of number of operations. Similarly, followed by best time complexity, we also have average and worst time complexity. Average is omega and worst time complexity is referred with big O notation. Now let's take something simple. Let's take an array, and I want to find what is the best, worst and average time complexity to do certain work, to do some work. So let's take an array, and the simple thing I want to do is find out the time complexity to search an element in an array. So let's create a simple array here. Let's take an array, let's say with 5 elements for us. Let's take the values as 10. Right, so hope perfect. So let's take it as 10, 20, 30, 40 and 50. Perfect. Now the operation I want to perform is search. Now If I want to search an element that is 10, isn't it the best time complexity? Because when you search an element in the array, you go from left to right. You search all the elements from left to right. And if the element you're trying to find is the first element itself, then that's the best time complexity. You don't have to do many operations. So only one operation is performed. Only one time your search operation is performed. How do we perform search operation? We create a for loop with indices like I equals 0, I less than n, and I plus plus. Now, in this, we keep on searching. That is, if something like a of I is equal to key is what we search. If it is equal to key, then we say element found and we exit the program or exit the loop. Now, in this case, if element is found in the first index itself, that is first index is 0. If element is found in this particular index 0, let's just write these as well, index 0, then number of times this operation is performed is only once. Since it is only performed one time, you can say this is the best time complexity. You found the element in the first place itself. So you can say best time complexity here for an array to search an element is theta of just 1. Just 1. Now let's go for average time complexity, where we'll use omega to do the same. Now in this case, on an average, your element can be anywhere throughout your array. Your element can be the first one, second one, third, fourth, or fifth. Let's assume on an average, your element is the fifth one, last one. It is found. We are talking about the element is found in the worst case scenario. It is the last element. So when the element is found over here, let's say for example, then you may need to perform once, that is not the key. Second time, that's also not the key. Third time, by increasing that, that's not the key. Fourth time, that's also not the key. Fifth time, that is also not the key. So whichever is the fifth time, let's assume this is the key. We are finding the last element. Whichever is the key, once you've found that, you can basically assume that that is your average time complexity. So if there are n elements, you can say n could be your average time complexity. You could find it anywhere between here that we may not know, but I'm just taking this. We don't use best or average most of the times. Our major point is to learn worst time complexity, which is the most important task. Now let's look at worst time complexity here. For instance, let's start with this. Let's say the key we are supposed to search, let's assume the key we are supposed to search is 75. Is the element available in our array at all? No, it's not. So when you search for this, first element, that's not the key. Similarly, second element, that's not the key. Third element, not the key. Fourth element, not the key. Fifth element, not the key as well. So you've performed 5 operations for 5 elements. Of all of those 5, you couldn't find it. Are there any more elements in the array? No. I less than n condition will become false because 5 less than 5 is no longer true. So it exits your for loop. And when it exits where you've given a key which is not found in your array, you can say that even then n operations are performed at maximum. So here you can say the number of operations performed in the worst case complexity is n. So worst time complexity for searching an element in an array is n. So this is how we basically find worst time complexities. So we often do this to find for search operations and insert operations, delete operations, and access operation. So for these 4, we generally end up finding worst case complexities because this is what we do often. We perform search, insert, delete, and access often when it comes down to programs. So let's take this one case. Worst case complexity for searching is n. We got to know in worst case, n number of operations will be done. Let's just take a look quickly at insert, delete, and access. So if I am inserting an element, let's try to figure out how to do that. let's see what will be the worst case complexity to insert an element. If I want to insert an element in the first index, then it's, let's assume we want to insert something in the first index. Now here's the catch. If you want to insert something in the first index, first thing, let's say we have one more space to insert another element over here. Now, if I want to insert here, it's very simple. I just go to A of 5 and insert 60. But if I want to insert something at the beginning of the array, let's say I want to insert 5 over here, 5 over here. If I want to insert 5 over here, I need to move all these elements to one step ahead. So let us try doing that. So first, let us take this 50 and move it to the next spot. One operation. Let us take 40, move it to the next spot. Two operations. Let us take 30, move it again to the next spot. Three operations. Let us take 20, move it again to the next spot. Four operations. Let us take 10, move it again to the next spot. Five operations. And the sixth operation, let's assume, is to insert the element over here. Let's say that is something like 5. Now, how many operations did we perform? We performed 5 operations to move elements. To move elements, we performed 5 operations. Then the sixth operation was to insert element. So when you perform these 6 operations, of course, given that you had 5 elements, you performed 5 plus 1 operations. So it should be big O of n plus 1. But remember, we are talking about big O, which stands for worst case complexity, worst time complexity. When we talk about worst time complexity, we don't assume that there are only 5 elements. In the worst case, there may be 5,000 or 50,000 elements. If there are 50,000 elements, does adding 1 to it make a difference? Is this a big difference compared to 50,000? No, it's very close to it. When you look at the number system, from 0 to 50,000, for example, 50,001 is so close to it, you can practically consider it as 50,000 itself. So that is why when we have small constants like big O of n plus 1, we basically consider it as big O of n itself, because in worst case complexity, for large values of n plus 1 doesn't really make a difference compared to big O of n. But if you'd like to keep it as it is, in some cases you may, but most of the times this is what we do. So here you can consider it as big O of n. Now, the next thing, let's say I want to delete something. Let's say I want to delete 5 again. If I want to delete 5, I'll delete it. I'll have to move 10 all the way over. I'll have to move 20 all the way over. Then move 30. Then move 40. And then move 50. So you can basically get to know how many operations we have done. So we've done again 5 plus 1 operations. So, but you can consider it as again big O of n itself. So whether it's for insert or delete, the worst case complexity you can have is big O of n. So with this, let us write the same down as well, big O of n. Now let's go for the last one, to access. Now when I talk about accessing, if I want to access A of 4, do I need to go through all the elements and then get to A of 4? No, because by default we know how arrays work. Their pointers, they work as A of 4 will become star of A plus 4, which is directly going to access this address and get this value. We don't need to go through first element and then from first element go find where is second element, from there go find where is third element, from there go find fourth element, from there find fifth element. We don't need to do that. We just directly need to go to A of 4. So there's only one operation required in worst case complexity. Whether it is index 0 you're accessing or index 4 you're accessing, you only need to perform one operation, that is access this value. So worst case complexity when accessing a value is 1 itself. So with this, we can observe here that arrays are good when you want to access elements. But when you want to insert, delete or search, for insertion, deletion, or search operations, arrays are not good enough. Arrays are not very efficient. Because in the worst case complexity, if you have 100 elements, the moment you want to insert, you're performing 100 operations. The moment you want to search, you're again performing 100 operations. And the moment you want to delete, you're again performing 100 operations. So to solve this, instead of arrays, we have other data structures. This is what I meant by stating why there are so many data structures. Which data structures are we supposed to use? Because each data structure focuses on one aspect, time or memory. Arrays focus on a different way. Arrays don't focus on time when it comes down to these three, but only time when it comes down to access. So if you are doing a lot of searching, insertion and deletion of elements, then instead of arrays, you can use a different data structure. So we'll see that ahead. Followed by time complexity. Space complexity is measured in how many bytes you take. Because whether you use my computer or someone else's computer, this array is going to take the same amount of bytes. Assuming it's 16-bit, it's going to take same amount of bytes. Assuming it's 32 bits, it's going to take same amount of bytes, whether in whichever computer. Assuming that they're in same architecture. Now, with this idea, you can basically say for n elements, the space you're taking here, because there are n elements, let's assume each element is taking 2 bytes. So 2n is the space complexity you're taking. So this is how you can assume is the number of bytes you need to store an array. For n elements, for an array of n elements, we would need big O, or worst, or total space complexity is 2n. It's not worst or best case complexity. For n elements, you would always need 2n. So going ahead from here with this concept clear, let us move ahead to the next part of this to understand a little more about how they work. Now, since we got to know this, let's compare it with one more data structure so we can get to know how these things are operated with respect to time and space. But before we go on to that particular data structure, we should know that there can be many other data structures, many other linear data structures that can be created using arrays. Using arrays, we can create some other data structures. For example, we can create stacks. We can also create queues. So there could be questions based on even these. Where are stacks used in real life? Where are queues used in real life? Can you explain how stacks work? Can you explain how queues work? So let's try just going through this in short. So for those who may not know, a stack is basically when you put one thing on top of another. Let's say I have a number 10. I put 20 on top of it, I put 30 on top of it, I put 40 on top of it. So just like when you have multiple books on top of each other, you can't take this book at the bottom right out. To do that, you need to take out all the books ahead of it, all the books above it. So the basic idea that happens here is, in a stack, if you want to take out any element, you have to take out the topmost element only. If you want to insert an element, you can't insert anywhere in between, you can insert only at the top. So your time complexity changes because you are giving more conditions, more constraints to an array. You're giving more constraints to an array. So your time complexity entirely changes compared to an array. Let's see how exactly it does change. So in short, think of it like this. A stack is where you can insert elements vertically. This is only for our representation. In computers, memory, everything is sequential, whether horizontal or vertical, it doesn't matter. Everything is stored sequentially in RAM. So let's say, since the stack is empty, there are no elements here. If I push an element, in stack we use the word push to enter or insert an element, and pop to remove or delete an element. So let us push an element into the stack. So if I'm pushing the first element 10 into the stack, it goes all the way down to the bottom of the stack and gets placed here. If I push one more element over here, it gets all the way to the bottom above 10 and gets placed here. So similarly, whenever we insert an element, it gets placed at the topmost value. So every time I insert an element, it only inserts at the next space available. Will I need to move elements to insert like we did in array? No. So when we talk about insertion, what is the worst case complexity? It's 1. It's no longer n, because whether I want to insert here or here or here, I'm only doing one operation. Because in a stack there is a variable called top, which will always store which index are we at. By default it will be -1. When you want to insert first element, top increases to 1, top increases to 0. This is your index 0, 1, 2, 3 and 4. When you want to insert the first element, top increases by 1 and goes over to that index, and that is where you insert your element as 10. Then when you want to insert the second element as well, even then top increases by 1 and you insert the second element over here. So for each operation, for each index that you're inserting, whether it's 0 or 4, you're only performing one operation. So its insertion is big of 1. Similarly, if you want to delete an element, I can't delete this element. I only have to delete the topmost element. When I delete it, top reduces to one value, that value gets deleted. So even when I perform delete or even when I perform pop, the worst case complexity is only 1. So you can see in certain situations this is useful. But why would I use stack instead of an array? Why would I put such constraints in the concept of array? Think about this. In computers, when you do undo and redo, you use stacks. So everything I've typed, if I type 1, 2, 3, 4, 5, whatever I'm typing is automatically stored in a stack. 1 is stored as first element in the stack, 2 as the second, 3 as the third, 4 as the fourth, 5 as the fifth element in the stack. So this is stored in undo stack. So if I press Ctrl Z, whichever is the topmost element in undo stack that is removed, that is placed in redo stack. Then again if I press Ctrl Z again, topmost element is removed. Then again topmost element, then again topmost element, then again topmost element. When I press redo, it will go to the opposite, to the redo stack where all the values are stored. So in short, the idea is whenever you perform undo, whatever element is removed from undo stack is placed in redo stack. So if I type 1, 2, 3, 4, 5 as it is, and I undo this, the moment I undo this, 5 is stored in the redo stack. Then the moment I undo this, 4 is stored in redo stack. The moment I undo this, 3 is stored in redo stack. The moment I undo this, 2 is stored in redo stack. The moment I undo again, 1 is stored in redo stack. Now when I start to redo, whatever is top in the redo stack, that will be pasted first. Then when I type redo again or Ctrl Shift Z, whatever is at the top, that will be stored back first. This is a live example, a practical example that you can see of stacks in real life. So why would I need to restrict my arrays to all these situations? Because of these reasons. Because in some cases, you don't need to access somewhere in the middle. Whenever I undo, do I want to undo last fifth operation? No, we only undo last operation first. We never undo even last second operation first. So that is how in undo and redo, for example, in stacks, since insert and delete operations, I'll just copy these right away. Since you want to perform insert and delete operations, you're not going to access anything further than this. It's just big of 1. But search, if you want to search for an element in an entire, let's say, stack, you're going to have to search all of them as usual. So that will obviously take big of n. So this is how undo and redo work in practical scenario, in real case, and stacks are used for it. So practically used to perform undo and redo operations in Word, browsers to go back and forward in links that you have opened, and so on, or a lot of other performances can be done. So this is how stacks are used. Similar to stacks, there is one more way you can particularly use arrays with a few more constraints. That is called queues. Now let's see how exactly queues work. Think of this. Let's say we have, as usual, we'll just take the same thing, 5 elements, 10, 20, 30, 40, and let's take the last value as 50. Now, I'll take this as index 0, 1, 2, 3, and 4. Now, if it's a queue, we know how queues work. So, if I want someone to enter a queue, that person will enter as the first person in the queue. Then insertion will always be to the end of the queue. So, in short, if I have limit of 5 elements in the queue or 5 people in the queue, the first person, whoever comes to the queue, will directly go to the front of the queue. Second person who comes to the queue will go as the second person in the queue. The third person will go to be the third here, then fourth, and then fifth. So these are 5 elements of our queue. Now in this case, if you observe, since it's a queue, the first person will have to exit first. So when we talk about inserting, I will never be inserting in the middle of a queue. When 50 comes, when the fifth element comes, I'm not gonna take 50 all the way to the front. That can't be possible in the concept of a queue. He has to be at the last of the queue. So for insert again, our operation is just big of 1. So here in queue, unlike stack, in stack we only used a variable top because top was where we inserted and deleted as well. But in queue, we need to insert at the back end of the queue, and we need to remove people or remove elements from the front end of the queue. So that is why we need 2 variables which stores these indices for our reference. So we call them as front and rear generally. If you look at any tutorials, you will get to see that in the code of queue. Again, we are not going through code. We are not performing any coding within this because our aim is to only work through the interview questions that you can expect in face-to-face and how to solve them. So in the front of the queue, you insert elements. So if you insert the first element, that becomes front of the queue. If you want to insert second element, and so on, and it keeps on moving. So front is a variable which indicates which is the first element of the queue. Rear is a variable which indicates last element of the queue. If I delete this last element, then let's assume my rear value is now here, and so on. So we are clear where insertion happens and where deletion happens. So to delete an element, I will only delete the front value and front will move to next index. To insert, I will only increase the rear value and insert here. So again, for insertion and deletion, when it comes to queues, we basically have the same purpose. We have the same thing. That is, to insert and delete, we have big O of 1. I will not go through access within a queue. If you want to access an element, we basically need to access only the first person in the element, or we may need to access any index. We can directly go to that index and access. So that's not a problem. But if you want to search, again, it's big of n. So this is how queues work. So again, now where do we use queues in real life? Now you may have seen this a lot in real life. You may have observed this a lot, especially when it comes down to something called flash sales online. There'll be something like flash sales begin at 11 a.m. and only first 100 people will be able to get some product for like 5 rupees. Everyone else will be able to get it for, let's say, 500 rupees. So everyone is looking to be the first 100 people who click the button on the web page. So when you click the button, you are added to the queue. So the first person to click the button according to the server will be the first person in the queue. Second person will be second, third person will be third. They will keep on storing up to 1,000 people or something like that, or up to 1,000 people. Let's assume if second and third don't buy it, then whoever are the next 2 people, they are added into the queue by moving everyone forward. So this is just one example in real life where you have used queues, where people generally use queues. A practical example is flash sales in websites. So let's go ahead from here now, from stacks and queues, from arrays particularly, to something else. Now we saw that there's a particular problem in arrays. That problem was In arrays, it is difficult to insert and delete elements in worst case scenario. So to solve this, to overcome this, if your main aim is not to just access elements, it is to insert and delete elements mainly. In that case, you need to perform some different steps. So here's what those steps are. So instead of using arrays, you can rather use another data structure that is created that is called linked lists. Now, let's just try to understand what linked lists are to begin with. Let's take one simple case. So, I'm just going to take an array. If an array has two elements like 10 and 20 here, we know they are stored in continuous memory locations. But in a linked list, elements are not stored in continuous memory locations. They are stored in random locations. So if the first element is 10 here, second element will be stored in some other memory location. So let's say 20 is here. Let's assume 10 is stored in some location 100. Let's assume 20 is stored in some location 200. Similarly, there will be the third element, let's say, which is 30, that is stored in some address called 300. So when you have data stored like this, what you basically need to know is the first element cannot find the second element immediately next to it, because first element address, after that you may find the address 102 or 104 or something. There you don't have second element whatsoever. It's in a complete different location. So to find the second element, you need to store the address of second element here also. That takes more memory, that takes a lot of extra space, but that's all right for us, because our main focus here is not space but rather time. The real case usages of this I will explain ahead, but let us focus on just this much for now. So we have 10 which is stored in some memory 100, and along with this value we are also storing the next element's address, which is 200. And in second element, where which is stored in address 200, along with the value 20, we are also storing the address of the third element, which is 300. And here along with the element 30, we are also storing address of the fourth element. Since this is the last element, there's no fourth element, we can basically state it as null, as there are no elements ahead. So this is how linked lists work. Now, why do we need to do all of this? Why do we need to take so much extra space? Consider this. Let's assume there are 100 elements. If there are 100 elements in an array, if I want to insert in index 1 as in between 10 and 200, if I want to insert 15, then I have to move 99 elements ahead. That's a difficult task. But in linked list, all you need to do here is just create one more element which has the value 15. Before doing that, let's just move these graphically a little ahead. Perfect. So let's say we insert one more element in some random memory location 15. Let's say it is inserted in some random memory location 400 now. So what we will do here is the next address for 15, we're going to store it as 200. So this will point to second element. But first element should, instead of pointing to this, it should now point to 15. So wherever the address is stored in first element, instead of 200, we're just going to change it to 400. Now we have made this point, we have essentially created a new element in our linked list without a lot of issues, without a lot of problems. So we didn't have to move so many elements ahead, we didn't have to do all of that. So this basic idea or this usage of such concepts are done by linked lists. So this, the advantage, as I just want to speak out. So in short, the advantage we see here is that for insertion and for deletion, the number of efforts you're taking, the number of operations you're taking are less. So in real cases, when your when your importance is towards insertion and deletion of elements, if you're going to keep doing this a lot, then using arrays is more time costing. If that's okay with you, then all right. But if you want to reduce time but you have enough space, then use linked list. If accessing elements is your main concern, insertion and deletion isn't, then you can go for arrays. This is how we select data structures. So we had to learn this by learning so much, but you can expect a lot of questions asked within this, like where are stacks used in real life, what is best case complexity, what is worst case complexity, how do all these work. So once you get to understand these, you will be able to easily solve any or easily answer any interview questions when it comes down to these kind of things. So this is how linked lists are created. But now there is one problem here when we create linked lists, because in linked list each element has multiple values stored in them. One is, let's say, an integer value, another is, let's say, an address of next element. Now this whole thing must be stored in a single element, in a single name. So I can't use an array to do this, because if I'm using a character value, character takes 1 byte and its address may be lengthier. So in array, everything must be of same data type. I can't use an array, because if this takes 1 byte and this takes 8 bytes, then this can't be used within an array. It's not efficient. So we need to create our own data type which can store, let's say, an integer here, for instance, and an address here. So to do that, we can use structure. So you can just create, again, this I'm just stating because when it comes down to linked lists, you can get also a question: how do you create linked lists? So this is the simple way to answer them. In order to create a linked list, you just need to create a struct variables. You need to create your own structure based user defined data type. So struct allows you to combine different data types together to create a single element. So that's exactly what we will do here. So let's just call it a struct element, because each one of them is one single element, or you can also call them as node, because generally we call it as node when it comes down to data structures, that is each element of linked lists. So the first data we need is an integer called, let's just call it as value. So this is done, this is our first element. And the second element is an address which will store next address. I will call it as next. Let's just assume the name, I'll call it as next. And since it is storing an address, it must be pointer type. So I'll use star before it as well. So it's a pointer called next, which is going to store the next address. So here, let me point this out in a different way. When we are storing next address, let's say we have two values, just for our reference. So let's take this as 10, let's take this as 200, let's say this is stored in address 100. Let's take this as address 200, let's say it is 20, and the next address is null considering it's the last element. Now, if I'm storing 200 here, is this pointing to this whole element, or is this pointing to only this integer element? It's supposed to point to the entire next element, and this next element, which is a single element, is of type struct node. Since it is of type struct node, the pointer where the address is stored should also be of type struct node. So that's why what we're going to type here is the data type for this address will be struct node. So this is how we create an element in linked list. So in interview, if you do get a question, how do you create elements in linked list, what exactly do you do in order to create elements in a linked list, this is exactly what you would need to answer. So going ahead from this, the basic idea here is, let's take this for instance. using structures most of the times, and you also have a clear idea of how they are stored. So in interview, if they ask you, can we create a linked list, can you create a linked list with multiple elements, if they just ask like I don't want just one integer, I want two integer, sorry guys, yeah, so I want two integer values stored in each element, let's say 10 20 here, 30 40 here. Can we do this? Of course you can. You just need to do something called int value 2 here as well. So it's going to store two integers. So this can also be very easily performed. So going ahead from here, let us now go on to the next part of this. So again, as always, let's take these operations over here for linked list. So when we talk about linked list, search operations, of course, you need to go from one element to another element. If you have, let's say, three elements, I'm going to take the exact same example again. That is of three elements. Let's say we have 10 here, storing address of the next element. This should be 100, let's assume, and let's say we have in 200, let's say we have 20 storing address of next element, and let's say along with this we have 30 here being the last element. So in that case, if you want to search for the element 30, you need to search for the element over here, whether this is the key. If not, go to the next address, search if this is the key. If not, go to the next address, search if this is the key. There it is. So you need to perform search in the same way as before. So for search, you have got big O of n. But for insert and delete, we won't consider it as big O of 1. We consider it as big O, sorry, we don't consider it as big O of n. We consider it as big O of 1. Because if you know where you need to insert an element, I'll repeat this. If you know where you need to insert the element and you have the address of that place, you can easily insert without moving elements ahead. So we consider it as big O of 1 itself. But if you want to access, we consider it as big O of n. Because if you want to access the last element, you have to move from first element and so on to get address of last element. In an array, you can just do a of 2 to get the third element. But in this, you cannot do that. So in a linked list, you need to go from one element to another element until you reach the last element. So that is where you say that your accessing of operations will also take a long time. So where exactly do we use this, or where in real life will we use linked lists? Now take this for instance. Before understanding where we use a linked list in real life, I'm going to give you one more example of a kind of linked list. So in this linked list, we only had address of next element. Similarly, you can create your own structure data type, user defined data type. Let's call it as node, and let's say we have something like int data here, and let's say struct node will have the next address stored in next, a variable called next. Similarly, we're also going to have one more address that is called struct node previous, which is going to store the address of previous element. So in that case, what you can state here is address of next element is also stored with each element, and address of previous element is also stored. For the first element, address of previous element will be null. For the first element, address of next element, let's say will be so let me just point this out. Right. So for the first element, let's say address of next element here is 200, but address of previous element here, since it's the first element, there are no previous elements, you can point it as null. Similarly, you can take second element as well, that is 20, and address of previous element of for 20 is the one before it, that is 100, and address of next element, let's assume it is 300, where in 300 we will store the element which is 300 or 30, and the address of its previous element is 200, and since it's the last element, next element will be null. So this is where you can perform forward transition as well as backward transition here. The advantage, because you have the address of the next element as well and the address of the previous element or previous node within your linked list as well. So as long as you have, as long as you're in one element, you can go back to the previous one and you can go back to the next element as well. So when we talk about all these things, which are, these are called doubly linked list or double linked lists, where you have addresses of next and previous elements are stored with the current element. So this particular concept, when we talk about this as a double linked list, are utilized in real life as well. But the question comes up as, where do we use them? Think about this. Think about a folder in which you have, let's say, your phone's gallery. As you can see, when you open the gallery app, you're going to see tens of images, and the moment you open one image, you can either swipe in any directions. If you swipe it left, you go to next image, because this is swipe to the left. If you swipe right, you go to the previous image. Now the previous image will not be stored in immediate previous memory address. The previous, if the current image is stored in some memory address 19978 or something like that, its previous image in the gallery can be stored somewhere in memory, some different folder where it is 173210 or something like that, and next one may be stored in 153280 or anything like this. It could be anything. So in that case, when you swipe either to the left or to the right, you're not going to the immediate next memory address. Instead, you're going to some entirely different address, and these can be used and stored in a double linked list to go in either of the direction. And similarly, when you only want to go in one direction, you can use it as a single linked list. So this is one fairly simple example like image gallery, where we often use doubly linked lists. So for example, you have thousands of images. So image viewer gallery can be used for this to swipe left or right to go to next or previous image in some other memory locations. So all of these are useful in some real case scenarios, and we need to choose the data structure based on where are we going to implement it, where are we going to use it, and so on. So there are a lot of such operations that can be performed. Now that we understood this, um, before going on to a little more about linked lists, before we go on to a little more about linked lists in terms of interview questions that you can possibly expect, what we're going to do here is just look at the difference between some search operations. So let's just go through a couple of search operations to begin with. Now we know we have linear and binary search. Now we know binary search only works when the array is sorted. If the array is not sorted, you cannot do binary search, you have to resort to linear search. But when the array is sorted, binary search is much faster. It's much faster. Let's see that with an example and try to calculate time complexity of the same. Because if they ask you, how do you define, what do you know about searching techniques? What are the different searching techniques that you have, and which is better and why? So you can basically say that linear search is good when it comes down to, I'll just point this out, linear search and binary search. Linear search is good when the array is sorted, not sorted. Binary search is better when array is sorted. Now, how exactly do they work? So I'm just going to take one pretty quick example. so that we don't go through it for a longer time. Let's just take it like this. So let's take some elements here like 10, 20, 30. Let's assume it is sorted to begin with. Let's assume it's not sorted. Let's say, for example, we have already 20. Let's take it as 25, 37, 68, 81, and 03 and 01. So if this is the array, since it is not sorted, you have to, if you want to search for 01, if you want to search for just one, forget that there's zero that's existing here, don't worry about it. If you want to search for just one, if it is sorted, you can go, you can say that one is the lowest element, you can find it at the left. That is one way you can do it. But it is not sorted. Any element can be anywhere whatsoever, so it makes sense to search from left to right, because one you can even find here or here or here or here. So that is why we perform left to right operations. But on the other hand, let's say if the array is entirely sorted, let's say something like this, 50 and then 60 and then 70, 80, 90 and 100. Now in this case, since the array is sorted, if I want to find 100, I know this is 100 is a larger number. There's no point in searching at the start. I can search at the end. Now how is that performed? This is where binary search comes into picture. Binary means two. We know binary is where 0 or 1. There are two parts. So in binary search, we're going to divide our array into two parts. That's how it works. So in linear search, just to take an example of this, in linear search, if I want to find 100, I need to perform 10 searches, because I need to perform from left to right searching function. So for 10 searches, you can basically say big of n is, or worst case complexity is n, because if you want to find 110 also, you are going from left to right, which performs 10 searches, it's not found. Now let's do the same in binary search. When we talk about binary search, let's take indices 0, 1, 2 up to 9. So in a binary search, if you're finding an element, the first thing you're going to do is find which is the middle of your entire array. The middle is found by length by 2. Length of the array is 10. 10 by 2 is going to give us 5. So I can say middle element of the array is index 5. So the first step I will do is go to the middle element and search whether this is equal to our key. Let's assume our key is not 100 but 110. We're going to search if this is equal to the key. It's not equal to the key. It is lesser than the key. So since our array is sorted, we know all the elements to the left of it are also lesser than this element. They won't be available here whatsoever. So what you can say here is your element 110 will not be found here or here or here or here or here or even here, because 110 is greater than the middle element you're searching. So once you've done this, you've basically eliminated 6 elements within one search. You basically eliminated 6 elements in just one search. Now once this is done, you go for the next step. The next step is to find between these. Let's take the index 6 and there are 9. So take 6 plus 9 by 2. When you perform this, you basically get 15 by 2, which gives you 7.5. Let's assume only 7 as integer part and consider this as the middle of our new available array. Let's see if this is equal to our new middle. Is it? No, since it is not. Since it is greater than this also, don't consider these two. Move the middle of the array now to the next part. So 8 plus 9 by 2, you're going to get a value which is 16.5 by, 8 plus 9, you're going to get 17 by 2, which you can take it up as 8.5. So let us assume that is also 8 itself. So you can search here now. So the larger the array, the more values get reduced at each time. So even since this is not equal, this is greater than it, let's go ahead to search for the next element. So when we do this, we found that 110 is not even the last element. There are no elements ahead of it. So you can basically stop here. So did we perform 10 operations? No, we just performed 1, 2, 3, 4 operations at maximum. So this is much better than linear search when there are a lot of elements. But how will you measure time complexity here? Because it's slightly difficult to measure time complexity here. Let me take a different case. Let us take a different example just to measure time complexity here. So let's assume we have so many elements that I'm just gonna um, display them as a box here. Now, let's say we have 16 elements in our case. So if I have 16 elements in binary search, my first step to do is to divide them into two halves. One half will have 8 elements, another half will have 8 elements. Now, when I search the middle element, if the middle element is lesser than my key, I'm gonna stop searching for one half of the array. I'm not gonna search within one half, it's discarded. I'll only search in the other half. In the other half, I'm again supposed to divide it into two parts. So I have searched only one element so far. Now I'm searching second element by dividing it into two halves. Now if I didn't find it here also in one half of it, I'm again going to discard it and consider the other half, divide it again into two parts. Let's consider it as 2 and 2. So one search, two search, now it is the third search. In the third search, are we finding it? If we are not finding it in one of them, discard that as well and only search in the other part. If you can't find it here, only search in the other part, which will be 1 and 1. So here when you divide it equally, it should be in either one of these. So when you search in one of these, if it's not there, then go to the other part. There's only one element, search there. If it's not even there, then stop. So how many searches did we perform? 1, 2, 3, 4 and 5. So we performed 5 searches in total for 16 elements as input. So for 16 elements we performed 5 searches. Now how can you write this as a formula? How can you write this in worst time complexity? It's not easy. You can't just say it's something like n by 2 or n by 3 or something like that. That's not the case here. It's not n by 2. If it were n by 2, it'll be 8. It's not n by 2. So when you get 5 here, the idea here is, since you're going to divide by 2 every time, it is basically 2 to the power of 5 that gives you 16. Oh, sorry, 2 to the power of 5 that basically gives you 32. So in such case, in short, what we generally do is, it's very close to that. So you can basically say most of the times, if you have 16 elements to be searched, you can just take it as 2 to the power of whatever n comes up, that n is the amount of times, which is very close. That's why we consider that as the number of searches. So in order to do this, in order to get this value, I need to take 2 over here because n is to the power of it. So to do that, we just take it as log n base 2, where n is the number of elements. This will give you how many searches are needed in the worst case scenario. So in the worst case scenario, you need log n base 2 searches when it comes to binary search. That's the basic idea. So it's much more easier when we perform search time complexity, which is big O of log n base 2. It's always considered as base 2 here, not base e. In linear search, for worst case complexity for search, it is big O of n. So when sorted, you can always go for binary search. When not sorted, you can go for linear search. You can also bring up a question like, why can't we sort the array and then search? Isn't that better? Isn't that better than linear search? It is only better than linear search. This is a common question that has been asked as well. Isn't sorting an array and searching with binary search better than linear search? So to answer this in short, think about this. If I want to sort an array, I will take something around big O of something which is greater than n. Whatever it is, we'll learn about it later on. But just remember for now, to sort an array, you will need worst case complexity which is greater than n. And then to perform binary search, you're going to need log n. So when you add these two, first you need to sort, then you need to perform this. It is something greater than n plus log n. Isn't that greater than linear search? That's why we don't intend to sort it. Unless your intention is, after sorting it, I'm going to perform search many times. If you want to search many times over time, then you can sort it. If you only want to search once, there's no point in sorting it and then searching it, because the time complexity is going to be more than what is required. So this is only when search is to be performed many times. So going ahead from this, there's an easy way using linked lists to perform binary search as well. So that is called something specifically using the concept of trees. So to understand what is a tree, we need to start learning how these kind of data structures work, because there are many different kinds of trees that are available. So in real life, you're going to have leaves at the top and root at the bottom of the tree. But in this concept of a data structure, you'll have root at the top and leaves at the bottom. I will not go into much technicality about this, because when it comes down to interviews, you will be asked questions to learn your understanding and to get to know how you um, know the implementation or working of these. So trees are basically created using linked list concepts. So just like how we create doubly linked lists, the same concept is used even in trees. So in a tree where we consider the first element as root, so let's say first element is 10, this we consider as root. Now if each element in a tree has only two children, we consider this as the parent element or parent node. This will have two child nodes at maximum, assuming if it has only two child nodes at maximum, like 5 and 15, then it is called a binary tree. A binary tree only has two elements at maximum in its children nodes. That's the basic idea of it. And even 5 will have only two or either 1 or 0 elements at maximum under it. So let's take 2 here. So even 15, either 2, 1 or 0 at maximum. Let's take 12 and something like 17 over here. Now this is the simple example of trees. Now we'll just continue in just half a minute, so please await. So going ahead from here, let's take for this for instance. This is a binary tree that we have just created. Now there's one little concept you need to know. In any binary tree, if the left child of your root node is lesser than the root node, and if your right child of the root node is greater than your root node, then you call it as a binary search tree. That's the basic point. So left child whenever it is lesser than it, or right child whenever it is greater than it, we call it as binary search tree, because in such a tree we can perform binary search. So here, unlike binary search within arrays, you don't have to find the mid element by finding which is the lowest index, which is the highest index, add them, divide it by 2, and then find the mid element, then search whether the mid element is equal to key or not. If not, if it's not equal, then find low again, either greater than it or lesser than it, and start the whole step again. You don't have to do all of that in a binary search tree. In a binary search tree, you will start with the root. Root is generally the middle element of the tree. So in this binary search tree, you will go find the root first. You will check, so yes, you will check if the root is your key to be searched. If the root is less than your key value is greater than the root, then you will go to the right side of the root and check if this is the key. Let's assume I want to search for 12. So if I want to search for 12, in a linear search, I'll go here, 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 here. I'll find it as the fourth element, assuming. Let's take the last element itself, because worst case scenario is the best case for us to learn. So in a linear search, I'll go first element, second element, third element, fourth element, fifth element. I'll find 17 as the sixth element. But in a binary search tree, when I perform binary search for this, here's the basic idea. We find if it is the root node. 17 is not the root node, but 17 is greater than the root node. So we go to the right side. Then we search for 15 if it is the root node. No. So we will again go to the right side. Then we'll search if 17 is the root node. We found it, done. If 17 isn't the root node, if you want to search something like 16, for example, we'll need to go to the left of 16. But to the left of 16, there's no element. So that is where you'll stop. Now, if they're asked, how are trees implemented? How do you implement a tree technically? So this is basically how you do it. Each element is a structure element. So you have an element 10 which stores address of 5 to the left of it and address of 15 to the right of it. This is just our representation. In real case, it's just a struct element. Each one of them, will call it as node, which by default has an integer value. We call it as data, and a struct node element, which is a pointer called previous and another pointer called next. So when you do this, you have one pointer called previous where you can store left child's address. Instead of previous or next, we call it as left and right here. That is basically what we call here. So you can store one element to the left of it and one element to the right of it by using this particular way. So this is how binary search trees are created, using the simple concept of something that we have learned earlier on, which is binary search trees. So what we can observe here, what we can see here, is that we are using the same concepts that we learned in binary search, that is in terms of doubly linked list. I'm just pointing this out. What we have learned in double linked list, where each element will have address to the previous element as well as address to the next element. Instead of calling as address of previous and next element, we call it as address of left element and address of right element. In this case, 17, when it is stored, in case of 17, address of previous element will be null because there's nothing to it, and address of next element is also null because there's nothing to the right of it. So this in short is how it works over here. So this, continuing ahead with this, if you're able to understand so far, the next part that we need to know with, or the next part that we need to work with here in terms of interview questions that you can expect out of trees, is this. So if you can perform all these trees, if you can create all these trees, what is the real life usage of it, or where do we use trees in real life? Sounds simple. If you are able to create such a complicated data structure and we use it in a constant basis, where do we use it? Where exactly do we use it? So to understand this in short, think about this. You may remember compiler design. In compiler design, when you perform something like c equals a plus b, each one is tokenized and you're differentiating it as then c, then a and plus and b and so on. A lot of things you keep performing like this. So this is one condition or one place where you do use trees in real life. So mostly we do use it in compiler design and lot of core processes like these. Also, when we talk about the previous cases, I did not state some other real case scenarios where we use stacks and queues. Stacks can also be used a lot in real case scenarios such as postfix or prefix expression evaluation. So we know that instead of a plus b, we can write operand first and then operators in prefix evaluation as plus ab. Similarly, postfix evaluation, you can do it as AB plus. So these are performed, these are evaluated by a computer using stacks. So even this can be done, and also there's a problem called Tower of Hanoi, if you're interested in searching about it, which is often solved using stacks in real cases. So that is the easiest way to solve them. So there are a lot of such problems which you can solve in real life using stacks as well. So going ahead from here, since we got to know what are trees and how trees are similar to linked lists, so we got to know that trees are very similar to double linked lists, except for the concept that in double linked lists, first element doesn't have anything to previous of it, that will be null. Whereas in trees, particularly we are talking about binary trees, first element will generally have two values, that is to left and to right of it. Instead of two values, I can just point it as two addresses. So these are some questions that you may be asked. These are some little things that you may need to know in order to solve and answer this. Now, following ahead from this, I will next just explain a little concept. I will not be going in depth within this, because if we do move in depth, we're just going to have to go through programming part of it, and we're not aiming to go towards programming part, because our aim and intention is only to learn from the interview purpose to just answer questions to begin with. So let's take one simple example of another data structure that is called graphs. So graphs are a new kind of data structures which are often used to represent social graphs or distances and so on. Take one example just to understand what they represent. Let's say we have four people. Let's say we have four people. Let's say the people are A, B, C, and D. So A is friends with B, B is friends with C, and let's say D is friends with B. Now, when we say A is friends with B, B also must be friends with A. So, in that case, there is symmetricity everywhere. You basically call it as a symmetric graph. So, if you consider this as a graph, like let's say A, B, C, and D, here also A, B, C, and D. Let's just create a few lines to mark it as a matrix, as a graph. So in this case, if A is friends with B, we consider them, since they are friends, we need to identify that either they are friends or not friends. Since it's a binary relationship, we're going to identify it either as 0 or 1. So to identify this, all that we're going to do here is, in short, A, let's assume A is friends with A by default, or A cannot be friends with A himself. Let's make that as 0. So is A friends with B? Yes. Similarly, B is also friends with A. Here, B is also friends with A. So here we also keep this as 1. Is A friends with C or D? No, A is not any friend with C or D. C or D are not friends with A either. So similarly, like this, you can just represent a graph either to just specify whether something is true or not, or if you have cities, the distance from A to B is 100, but the distance from B to A, because return route may be different, is something like 200. So if this is the case, you can just state it as, from A to B, it is 100. From B to A, let's just point it as 200. So A to B, you can say it's 100. B to A, you can state it's 200. So like this, you can create asymmetric graphs as well. So these kind of graphs, which can either be symmetric or asymmetric. So graphs can either be symmetric or asymmetric. They are often used to create and solve a lot of different problems, like for instance, finding common friends. Common friends, let's say in Facebook, you can just use a graph like this, the previous example we just took. So taking example here that A is friends with B and B is, let's say, friends with C. So since A is friends with B and B is friends with C, we can say A could be a mutual friend to C as well, and let's suggest this person to be friends to A. So like this is just one example that I'm just taking up, and since there will be a lot of zeros everywhere here, whenever a graph has too many zeros, we just call them as sparse matrices, because sparse means very less, very few and far between. The elements where you have values are very less, few and far between. So following ahead with this, the other basic things that we just need to know and understand when it comes down to these, let's just take a couple of examples, are when it comes to graphs, apart from this, you can solve it to you can use it to solve many real case problems like knapsack problems, or use chess problems, or even I've just missed out L here. Perfect. Or even solve many distance problems, like from city A to B is some distance, city B to C, and C to D is some distance, like this. And a person needs to travel all the cities. So how will the person start from A so that he can travel all cities by saving as much fuel as possible? What will be the direction, or what will which city should he go first? From there, should he go to D and then go back and go C, or should he go to C and then go back and then go to D, and how should he return back? So all of these are often calculated using graphs. So graphs are often used to solve many such real case problems, and to solve these real case problems, we use many algorithms, many algorithm techniques. So many algorithmic techniques. So we will see what those algorithms are, what those techniques are in the coming time. For example, to solve when it comes down to algorithms, we have something called dynamic programming, which has something called memoization and tabulation between them. So when we talk about dynamic programming, there's a lot that can be asked, and when it is this, again I'll state, is a very important question, because dynamic programming is something that every programmer should know, literally should know. So you can just expect a question like what is dynamic programming, and if you explain what is memorization and tabulation as well, then that just is better from your side, is what I would always say. So we'll take an example of that, and we will see the different kinds of algorithms that are sorting algorithms, which are the better sorting algorithms, which are the best ones, which one should you use at what scenario, and what kind of other algorithms that are there, like divide and conquer. We may not have known, but we have already used divide and conquer algorithms earlier. Then there is something like greedy algorithms. Then there are many other techniques when it comes down to algorithms. So you can also expect some questions on time complexity, particularly on sorting algorithms, which is the best sorting algorithm, which is the worst sorting algorithm comparatively, which takes more time, which takes less time. There's also other type of algorithm techniques like backtracking and so on. So these are the next things that we want to work through and learn through. But before going through all of these, now that we got to know the common types of data structures, we just need to take a couple of points here. So in these data structures, we get to know that here you have linear data structures and non-linear data structures. When we talk about trees and graphs, we generally term them as non-linear data structures, because we don't consider them as pointing in a sequential direction, because the trees can go in various directions, like this, like to the left, to the right, to the left, right, and so on. And similarly, graphs can point to in various ways as well, like this. So these are generally considered as non-linear data structures. The others we generally consider those as linear data structures. Now with this, in this session, we are now able to learn and understand what kind of questions you may expect from data structures. Now it may not be limited to these, but these are the most major and important questions that you may expect. In the next session, we'll go ahead with algorithms, not in detail, because we'll not be going through any coding of this, just only the basic things that we need to know to answer these. Followed by this, we'll just go through computer networks and operating systems, the most important questions that you may expect even in them, because a lot of companies do expect you to know networks if they hire you as a network engineer, and operating systems as a basic thing whatsoever. So these can also be answered by you if they ask you a question like, are you from computer science branch? So if you say yes, or even if you say no, they may just ask, how much do you know about computer networks, or how much do you know about operating systems? And they may particularly ask you some questions. Or even if you say, even if they ask what was your favorite subject, and they may ask from your favorite subjects a few questions, and you may have to answer based on them. So even in such questions, we will learn how to answer the same over here. So we'll see these in the coming session. So by the time, I'll just share all the concepts and notes till today's session for your reference, so that you can access these later on. This will be pasted in the description of the video, so you can access this link directly later on as well. So following by this, I'd also want to state directly that if you guys like these videos, go ahead, like and subscribe. The same for the effort, and you can also go through more of our videos, whether in aptitude as well as technical, in our channel. Subscribe to the channel as well to get to know a lot more contents as well. I'll just share this link here for now. This will also be shared in your references or in your description of the video later on for you to access. So thanks for joining in for our entire session. Make sure you do catch up with our next session as well, and keep subscribing and liking our videos. And if you are interested in going through our entire program on technical and aptitude and verbal completely to be perfectly trained for interviews, do check our description, contact us below, and we'll get back to you. So thank you.